Okay, at this point we've already looked somewhat in depth at the reactions of the halogenoalkanes with both water and with aqueous hydroxide ions. There are, however, a few more reactions that we want to examine before completing this topic on the whole. So if you want to go back and look in depth at the mechanisms of the reactions of halogenoalkanes with water or the halogenoalkanes with aqueous hydroxide, please go back and check the previous videos because that's covered in depth there. Right, okay, so in a previous video we have discussed the fact that the halogenoalkanes can react with ammonia solution, and the conditions for this: we need concentrated ammonia dissolved preferably in alcohol so that the halogenoalkane is not going to react with water present, and the whole thing has to be carried out within a sealed tube. So Rx, which is our symbol for a halogenoalkane with concentrated ethanolic ammonia. So that just means ammonia dissolved in ethanol and heated in a sealed tube. Now, remember, the reason for heating within a sealed tube is because if you do not have the sealed tube, the ammonia, which will vaporize, will just escape. And there's no way of containing that simply with a condenser because ammonia has a boiling point of well below 0. So a cold water condenser just isn't going to help condense it again. Now, it's important to note for this reaction to work properly, we want ammonia in excess, and we'll see why the excess is needed a little bit later on. So I'm going to just draw out the general structure of a primary halogenoalkane. So we're going to have RCH2 and then X, and our X is going to be delta minus, our carbon bonded to it is delta plus, and in the first step of this reaction, just as with any nucleophilic substitution, your nucleophile, which is your species usually with a lone pair, is going to be attracted to the delta positive carbon and is going to attack, which results in the breaking off of your delta minus X as an X minus ion. We say that X minus is the leaving group. So we end up with this. Now, this step here is actually stable. You can compare this species here to an ammonium ion. So if we have a look at this molecule here, we've got NH3, an NH3 group attached onto a carbon with a positive charge. Now, if we compare to ammonium, this is very, very similar, except what we've done here is this hydrogen is replaced with an alkyl group. Now, having an alkyl group there instead of a hydrogen, we know that alkyl groups are really, really good at donating electron density to anything that they're attached towards by something that we call the inductive effect. And so, as a result of this, the positively charged nitrogen in this NH3 plus group actually receives some electron density from the alkyl group that's attached to it. And this results in the positive charge in this species being spread out. over the molecule. And as we know, when we've got a charge within a molecule, if it can be spread out, that becomes more stable. So what we've actually produced here is a stable compound made up of two ions, a cation and an anion, the cation being an organic nitrogen species. And what we call this type of compound is an alkyl ammonium halide, where the alkyl ammonium ion is this species here. Okay, it's like an ammonium ion, but instead of just having 4 hydrogens attached to the nitrogen, you've got an alkyl group attached onto the nitrogen. And this thing is stable and can be purified. Now, so we end up at that stage with our alkyl ammonium cation, and if there is no excess ammonia present, you will just stay with this species. You just produce this as your product, and that's fine. It's stable, so it will happily just sit there. However, if we have excess ammonia, as we mostly do, what can happen is that the excess ammonia can act in a second step of this reaction, not as a nucleophile, but actually as a base, by which we mean something that accepts H plus from another molecule. So in this case, the H plus is going to originate from the hydrogen-nitrogen bond in this NH3 plus group breaking, and that would produce a H plus, but that is instantly picked up by the lone pair of the NH3. So it's important to be able to distinguish here. The NH3 in this step is acting as a base because it's not attacking a delta positive carbon, it's attacking a hydrogen and picking that up off the molecule. So this then takes us to the end step, the final stage of the reaction, where we end up with an NH2 group on our organic molecule, and then we have an NH4 plus ion, which has come from the ammonia picking up a H plus, and X minus. So we get a side product of ammonium halide being produced. Okay, so not an alkyl ammonium halide this time because this is just standard ammonium. Right, so let's have a look at how a few of these reactions might work out. So if we have a look at, let's say, 1-chlorobutane plus ammonia. So if we've got the ammonia not in excess, then we will have just one molecule of ammonia reacting with the 1-chlorobutane. So we would have CH3, CH2, CH2, CH2Cl plus NH3 goes to CH3, CH2, 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 NH3 plus Cl minus, and this would be known as butyl ammonium chloride. Okay, and that's your alkyl ammonium salt. However, if we do have ammonia in excess, which is the standard, then we've got a slightly different reaction. CH3, CH2, CH2, CH2Cl plus. Now in this case, if we've got excess ammonia, we get the first ammonia molecule reacting with the 1-chlorobutane as a nucleophile, producing our alkyl ammonium salt, but then there is a second molecule of ammonia that will react with the 1-chlorobutane as a base. So in fact we need 2 lots of NH3 here, and this time we will get CH3, CH2, 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 NH2 plus NH4Cl. So in this case, rather than butyl ammonium chloride, we've got butyl amine, which is an amine, the NH2 group being the functional group of this, and you've got ammonium chloride as a side product. Okay, so this is the standard situation for carrying out this reaction with the ammonia in excess, because usually we are looking to produce an amine from the halogenoalkane. Okay, and so just to summarize that reaction, it's good in organic chemistry to stack up certain reactions with certain similarities and then just do like a comparison of similarities and differences in your head. And we can see that with this reaction of halogenoalkanes with ammonia, there's some similarity to the reaction of halogenoalkanes with water. Both of them involve 2-step processes where the first step actually produces this organic cation, which then is broken down in the second step. The difference is in the reaction of a halogenoalkane with water, the cation that is produced in the first step, which has an OH2 plus group on it, that cation is fundamentally unstable and so does not need further encouragement just to spontaneously break down. In the case of the reaction of halogenoalkanes with ammonia, however, the cation that we produce is an alkyl ammonium cation, and this is actually quite stable, and therefore you require a good base to be provided to actually remove the H plus from that cation to produce your final amine product. And of course the base that we have present is the excess ammonia, that second ammonia molecule that doesn't act as a nucleophile but acts as a base to remove H plus to deprotonate the alkyl ammonium cation to produce the amine product. Okay, so a little bit of comparison there in that regards. Right, the next reaction that we're going to have a look at is the reaction of halogenoalkanes, RX, with ethanolic, KCN, and this is carried out in conditions of heating under reflux. Okay, so in this case, we've again got ethanolic conditions, so the solvent is ethanol rather than water, because we know that water will react to hydrolyze a halogenoalkane, so that would be an undesired side reaction. We can avoid this by using ethanol, which is less likely to react with the halogenoalkane. And we are carrying out the reaction heating under reflux. This is because both the halogenoalkane and the ethanol solvent are volatile, so if you are heating, those are going to evaporate. You need some way of containing them, so you use a vertical cold water condenser. Any vapors that are escaping during heating go into the condenser, cool, are condensed back to liquids, and are dripped back down into the hot reaction vessel. Okay, so that's explaining our conditions here. Now, in order to understand what reaction is going to take place, we need to first have a bit of an understanding of KCN as a reactant. And actually, I find the easier way to think about this is to understand KCN as a salt of hydrogen cyanide, with hydrogen cyanide acting as a weak acid. So if we had HCN, for example, and we reacted it with potassium hydroxide, we end up with KCN, which is a salt, plus water. Now let's start off by considering the structure of HCN. By simple consideration of valencies, hydrogen forming one bond, carbon forming four bonds, nitrogen forming three, we could draw out the displayed formula for this molecule. And when this acts as an acid, it's going to release H+, which, using a mechanism, we can show as this step here. Okay, so you get the H+ and the Cn-, and this is what is present in your KCN. Okay, now let's go into a little more depth and think about how this looks in terms of dot and cross diagrams. So we've got our hydrogen, our carbon, and then we've got our nitrogen. Now we've got a triple bond between the carbon and the nitrogen, so it's going to be 3 lots of dots, 3 lots of crosses, not drawn very well there, but you get the idea. And a single bond between the carbon and the hydrogen, so 1 dot and 1 cross there. And therefore, we can determine that, well, H+ has no electrons, so we don't really have to draw out the dot and cross diagram there, but the structure of the Cn- is going to look like this. The carbon-nitrogen double bond the triple bond does not change, so we've got exactly the same structure there. The nitrogen lone pair doesn't do anything, but the carbon now has a lone pair on it. Now, this gives us a species that acts very well as a nucleophile. Remember, for something to act as a nucleophile, it needs a lone, in most cases, needs a lone pair, an available pair of electrons for attacking a delta positive carbon. And its nucleophilicity is actually helped out by it being negative as well, which means that it's going to be attracted towards regions of low electron density, regions that are partially positive. Now, the question is, which of these lone pairs actually ends up being used in the nucleophilic substitution, in a nucleophilic reaction? Now, two ways of understanding it. Firstly, you can think of, oh, well, the carbon would have had 4 bonds, so that's the one that's going to be forming the bond, and therefore that is going to be the nucleophilic atom. The other thing the other lens to have a look at in terms of identifying which of the lone pairs is going to act in the nucleophilic substitution is to think about their energies. A lone pair on a nitrogen atom is going to be lower in energy than a lone pair on a carbon atom because nitrogen has more protons in its nucleus. So these electrons experience more attraction towards the nitrogen than these electrons experience towards the carbon. And therefore, these electrons on the carbon are more unstable, higher in energy, due to lower attraction to the nucleus. Therefore, these are the ones that are going to be the most reactive. Okay, this is the most reactive lone pair. So it's the carbon lone pair on the cyanide ion that is the nucleophilic lone pair here. Okay, so let's have a look at a reaction, and let's go with 1-bromopropane plus ethanolic KCN. So let's start off by drawing out our 1-bromopropane suitably. And we're going to do this mechanistically this time. So let's do CBr here, H, H, and then the rest of the molecule we're just going to simplify as C2H5 just to keep it out of the way because nothing's really happening on those two carbons. Now, the K plus ion is just a spectator, so it's present, but it isn't really going to do anything. The thing that we are interested in is the Cn minus ion, which I'm going to draw here, and we have to show the lone pair on the carbon, which is going to be involved in the reaction. Now, the carbon-bromine bond is going to be polarized, so we've got to do our delta plus and delta minus, and the lone pair is going to attack in at that carbon, and the carbon-bromine bond is going to break, depositing a pair of electrons onto the bromine. This then gives us K plus and Br minus as our potassium bromide side product. So that's an inorganic side product, and we are going to get an organic product which looks like this. This is a class of molecule known as a nitrile, with the functional group C triple bond N within it. This particular nitrile is going to be butane nitrile because we've actually got 4 carbons in here. 1, 2, 3, 4. So this actually shows you an interesting aspect of this particular reaction in that it actually forms a new C-C bond. These are quite difficult to produce in a controlled manner, so it's always worthwhile noting when you have organic reactions that can actually extend the carbon chain. So this reaction is useful because, first of all, it gives you a controlled extension to the carbon chain, forming a new C-C bond, but also it adds a carbon to a carbon to nitrogen bond is added to the molecule. Now, this you can leave as a nitrile. It can easily be converted into other functional groups as well. So C triple bond N can be converted into a COOH group by a hydrolysis reaction. And it can also be converted into an amine by a reduction reaction. Though actually, I should be a little bit more careful here, because in that reduction reaction we do add on more hydrogens to that carbon, so you must not forget that. So that becomes a CH2 NH2 group. Okay, so this functional group is actually quite useful, and even we can use it to go to an producing an amine. Now, when you get onto the amines, you'll consider the different methods for producing an amine from a halogenoalkane and weigh up some of the pros and cons. We're not going to discuss that just at the moment, though. The last reaction that I want to introduce here actually uses the same reactant of one of the previous ones that we have discussed, that of the hydroxide ion. So we are aware that if you start off with a halogenoalkane and we react this with OH minus ions, and the conditions are aqueous, so we've got an aqueous solvent, which just means that there has to be some water present, we end up with an alcohol, and we get a side product of a halide salt. This particular reaction occurs via the mechanism of nucleophilic substitution. However, if we alter the conditions just a little bit, we can get another type of reaction occurring entirely. So if we have an ethanolic solvent, so based on ethanol, but here we have no H2O present, so the conditions are anhydrous. Instead of getting an alcohol, we actually end up with an alkene. Okay, the side products in this case, we do get a halide salt again, but we also get water as a side product. Now, this particular reaction has a completely different mechanism, and this is what we refer to as an elimination mechanism, where a small molecule is removed from the organic molecule and becomes a side product. In this case, the small molecule being, you could consider the small molecule being a hydrogen halide, which is then neutralized by the hydroxide as a hydrogen halide. HX is acidic. If that's produced in a mixture containing hydroxide, that's going to neutralize to give you water and the halide salt, which is the side products that you actually see. Now, the nucleophilic substitution and elimination mechanisms are what we would say as being in competition with each other. Even if you've got aqueous conditions, you're still going to get a tiny little bit of elimination happening. Even if you've got ethanolic conditions with no water present, you will still get a tiny bit of nucleophilic substitution occurring. So there is kind of a balance of the two reactions happening, producing mixtures of the two organic products that are possible here, the alcohol and the alkene. But by changing the conditions, you favor one product over the other. So if there is no water present and you're working in ethanolic conditions, anhydrous ethanolic conditions, you will tend to favor producing the alkene. If you are working in aqueous conditions with lots of water, you will tend to produce more of the alcohol via nucleophilic substitution. Right, so let's have a little bit of a look then at the elimination mechanism. So let's carry this out with, let's go with iodoethane plus ethanolic potassium hydroxide, and this is heat under reflux. Okay, actually, given that I want to do this as heating under reflux, I'm not going to use iodoethane. I am going to go for instead, let's make it 1-iodo heptane. 1-iodoheptane. Now, the reason I'm going for this option is because if we were using iodoethane, the reaction would work. We would produce ethene, though, and ethene would not be contained by the conditions of reflux, so it would kind of escape and go into the room, which would not be very sensible. If you were using iodoethane and therefore producing ethene, you would need a slightly different reaction setup, which would be able to collect the ethene gas that would be produced, as reflux is not going to contain it because ethene has a boiling point well below 0 and can't be condensed by a cold water condenser. Okay, so let's have a look at how this reaction would work. Now, it's important to understand that within this course, you do not actually need to know this mechanism, but it's helpful to have a little bit of an examination of what's going on here for comparison with the nucleophilic substitution reaction which can take place. Okay, now given that we are going to form an alkene, we know that there are at least going to be 2 carbons involved in this particular mechanism, because we are going to be forming a carbon-carbon double bond within the mechanism. So I have to draw out the displayed formula around these 2 carbons. Now, I'm going to simplify the rest of the molecule, however, as let's not go for structural formula because that's even going to be too long here. Given that we've got heptane, there's going to be 5 carbons, so that's going to just be written as C5 and then C5H11 group. Okay, so we don't need to see the structure here because these carbons and hydrogens are not going to be involved in the reaction. Right, just as in the case with the nucleophilic substitution, the part of the potassium hydroxide which is going to be reacting is the hydroxide ions. Now, this time, though, the hydroxide is not going to act as a nucleophile. It's not attacking a delta positive carbon. The hydroxide actually acts as a base being something that accepts H+ from the molecule. Now, in this case, the H+ that we're accepting is a hydrogen from the adjacent carbon to the iodine. And when this hydrogen is accepted, the electrons from the carbon-hydrogen bond actually are transferred into the adjacent carbon-carbon bond. Now, no need to think about this too much in depth. It is beyond the scope of the course, but you can see here that with this particular curly arrow, you produce a H+ as electrons move away from this hydrogen, and you're going to produce a carbon-carbon double bond here. Now that H plus is instantly picked up by the OH minus. Okay, so OH minus comes in, forms a bond here. This bond breaks, forming a carbon-carbon double bond, and then your iodine on the other side breaks off as an iodide as your leaving group. So this actually gives you a one-step mechanism. Now the K plus spectator ion is floating around at the end. So what do we end up with? Well, we get a C double bond C. We have two hydrogens attached on this carbon. We've got our C5H11 group attached on this carbon, along with a hydrogen as well. We've got H2O, which has been generated from the OH minus, picking up the H plus, and we've got K plus and I minus generated. So where do each of these come from? So this generates our water. And this generates our potassium iodide side product. So the overall word equation for this reaction is going to be 1 iodoheptane plus potassium hydroxide goes to hept 1-ene plus potassium iodide plus water. Okay, and this is going to have a similar form for any of the halogenoalkanes. Right, now one thing to consider, of course, if we've got iodine in the number 1 position on the halogenoalkane, there's only one alkene that can be produced from this, because there's only one adjacent carbon-carbon double bond. If, however, I had 2 iodoheptane, so that would look like this, and C4, oh no, okay, if we had 2 iodoheptane and we reacted it with KOH in ethanol, we can actually get 2 products, because there are 2 adjacent carbons that are next to the carbon with the iodine, and so there are 2 positions where you can produce the double bond, and so you end up with a mix of products. You would end up with some of this, but so this would be hept-2-ene, but you would also end up with some hept-1-ene as well. Okay. So that's simply because the carbon with the iodine bonded to in 2-iodoheptane has two adjacent carbons with which a doubled up carbon-carbon bond could form, and so there's going to be a mixture of the alkene products that are generated. Okay, so at this point we're about ready to put together our summary of the reactions of the halogenoalkanes. So let's start in the middle. So, halogenoalkane, and we're going to begin with how we can produce it, and we know one route of producing a halogenoalkane so far, which is from an alkene. Alkenes can be reacted with a hydrogen halide, HX, via an electrophilic addition reaction. We also know that halogenoalkanes can be converted back into alkenes. So here we've got KOH, ethanolic, and this is under reflux. And this is an elimination. Okay, so this gives you an idea of addition and elimination as two things that work against each other. Okay, right. Now, kind of as a diversion from that reaction, we can have KOH in aqueous conditions, and again under reflux, and this gives us an alcohol, and this is via nucleophilic substitution. Okay, and let's actually put on some of our side products here. So the other side product from this is going to be KX and H2O is made as a side product, and with our nucleophilic substitution we just get KX, our hydrogen halide, as a side product. Our potassium halide as a side product. Right, another way of course of making an alcohol is to warm the halogenoalkanes with H2O, but this time instead of getting KX as a side product we get HX, a hydrogen halide, as a side product. Okay, then we've got the reaction of the halogenoalkanes with excess NH3 in an ethanolic solvent and heat in sealed tube. This is another nucleophilic substitution. And this gives us an amine. We also get a side product of NH4X, ammonium halide. You should probably note that this reaction with water is also nucleophilic substitution. Okay, and the last reaction that we can add on here is, of course, the reaction with KCN ethanolic solvent and heat under reflux. This is again a nucleophilic substitution, and this gives us our nitrile, and we get a side product of KX. Okay, so just to bring those out, let's highlight the organics. So we've got our halogenoalkane in the center, which can be interchanged with an alkene back and forth, and be converted into an alcohol by two different routes. We can produce an amine, and we can also produce a nitrile. Okay, and that is essentially what we need to know about the halogenoalkanes at this stage.